Alright, we're on page 60, ready to talk about some math. Again, page 60. And we're going to start with something called specific heat. Specific heat is the amount of heat that it takes to raise the temperature of 1 gram of substance 1 degree Celsius. So basically, this is like, for instance, if you have 1 gram of water, maybe just sitting in a cup. 1 gram of water. And maybe that 1 gram of water is at 25 degrees Celsius. Well, if you want to make that be 1 degree Celsius hotter and be 26 degrees Celsius, you're going to have to add some amount of heat, Q. We talked in the previous page that our abbreviation for heat is Q. That takes some amount of heat, and that is specifically the specific heat, and we call it the specific heat because it is for specifically 1 gram going 1 degree Celsius. So instead of Q, we actually end up calling that lowercase c when it is specific heat. Heat in general is Q. The specific heat we're going to call C. Excuse me. So, a low specific heat happens for matter that gains or loses heat quickly, like the tiles on the space shuttle. Those are designed to be able to lose heat really rapidly so that when the space shuttle re-enters the atmosphere, it doesn't like overheat the whole shuttle and melt. Those tile panels on the outside are able to lose heat really quickly, really rapidly, so that heat dissipates instead of going inside the shuttle and like baking the astronauts inside or whatever. A high specific heat is matter that loses or gains heat slowly. This is like water. If you've ever taken room temperature water and tried to boil it on the stove, it takes forever, and that's because water has a really high specific heat. In fact, water has a uniquely high specific heat compared to other substances. This means that it takes a lot more energy to make water be 1 degree Celsius hotter than it takes to heat other substances 1 degree Celsius hotter. So, for instance, if you have a frying pan, I'm not a good artist, pretend this is a frying pan, okay? And there's oil in the frying pan. Heating the oil up from room temperature is really fast, but if you have like a sauce pot that you're doing like pasta in for like mac and cheese, and there's water in there, it will take the water a very long time to boil, whereas the oil will start popping very quickly once you turn the stove on. You can get the oil to boil, it's fun to say, you can get the oil to boil with a very small amount of heat, but if you want the water to boil, it's going to take a much larger amount of heat. This is supposed to be fire from the stove. It's going to take a lot more heat to boil water than it takes to boil the oil. The specific heat of water is 4.18 joules per gram degrees Celsius. Those units are joules for energy, how much energy it takes for every 1 gram to be 1 degree Celsius hotter. We will use this piece of information to find specific heats of other unknown things. We're going to come back around to that later. For now, let's talk about our variables. When we talk about heat, we're talking about thermal kinetic energy. Our symbol, our variable for that is going to be a lowercase q, and it's measured in units of joules, which we abbreviate capital J. This is a new unit. It's an energy unit. We measure energy in joules. Actually, it's not totally new. We did talk about joules in unit 4 way back when we were talking about light energy specifically. Well, now we're talking about heat energy, but all energy is still going to be measured in units of joules. But when it's heat energy, we're going to use the symbol Q to talk about specifically heat. Mass, or how much substance there is, we're going to use lowercase m, and we're going to measure mass in grams. Specific heat is the amount of heat it takes to raise the temperature of 1 gram of substance 1 degree Celsius. That's what we were just talking about at the top of the page. Again, specific heat symbol is a lowercase c, and it's measured in these units of joules per gram degrees Celsius. That basically means how much energy it takes for every 1 gram to be 1 degree Celsius hotter. The definition is right there in the units. And change in temperature, it's its own calculation. Final minus initial temperature, the end temperature minus the start temperature. Its symbol is delta T, where this triangle is not a triangle. It's a uppercase Greek letter called delta, and it means change. As you take more math and science classes, you're going to see delta more and more often, and it's always going to end up meaning change. Change in temperature is going to be measured in units of Celsius, degrees Celsius. So our formula is that Q equals M times C times delta T, where Q is our heat. You calculate Q by taking the mass, the specific heat, and the temperature change and multiplying them. Usually when I write this formula, I just write Q equals MC delta T like this. When I say it out loud, I will call this Q equals mcT, because the delta kind of looks like an A, so it kind of looks like this spells out mcT. Please note that's not actually an A, it's a delta. It just means change, but just to make it easier to say out loud, I usually will say Q equals mcT when I talk about this. Let's try a couple examples. Like number 1 here says, how much energy is required to heat an iron nail with a mass of 7 grams from 25 degrees Celsius until it becomes red hot at 750 degrees Celsius? The specific heat of iron is 0.46 joules per gram degrees Celsius. Is it endothermic or exothermic? Well, if you look at the next page, you may notice our old friends, the guess boxes, are back. Yay! Remember that the G in guess box stands for given. The U is where we write our unknown. The E is where we write the equation. The first S is where we substitute. And the last S is where we write our solution, where we solve. So let's look at our givens and number 1. Number 1 says how much energy is required to heat an iron nail with a mass of 7.0 grams. So this mass of 7.0 grams, that's our M. It says from 25 until it becomes red hot at 750. So 25, that's our starting temperature. We're going to call that TI for initial. It becomes hot at red hot at 750. That's our final temperature. We're going to call that TF. Then it says the specific heat of iron is 0.46, so that's our C, specific heat. And those are all our knowns, all our givens. So we're going to put those in our guess boxes right now, where M is 7.0 grams. Our initial temperature is 25 degrees Celsius. Our final temperature is 750 degrees Celsius. Our specific heat is 0.46 joules per gram degrees Celsius. And then the question asked how much energy. Energy, we are measuring this energy in terms of heat, which our variable for that is Q. So if they're asking how much heat energy, they're asking us to find Q. And our units for Q is measured in J, joules. So I'm going to put a J here for joules, and I can also put J down here in my answer before I forget. We only have one equation in this unit. So, in fact, anytime you're using guess boxes in this unit, you're going to use the same equation. So you could literally write this equation every single time in all the guess boxes, all over the page, because this is the only equation that we have that goes in guess boxes for this whole unit. Okay, so that right there, if you're taking a quiz, as soon as you see the guess boxes, stick Q equals MCAT in those equation box. I'm even going to write it on the board. You don't even have to memorize it. Stick it in that box and you've already got yourself a point. So easy. Okay, just copy it off of the board straight into that equation box. From there, we got to start plugging some stuff in. We don't know Q, so that's our unknown. So in my substitute box, that's going to stay a Q. Okay. For M, my mass is 7.0, so I'm going to plug in 7.0. C, my specific heat is 0.46. I'm going to plug in 0.46. And then delta T, this is one variable, so I'm going to plug in one thing for that. But remember that delta T is the measured calculated change, and we calculate it by doing final minus initial for our temperatures. So since we had two temperatures here, we have to subtract T final minus T initial, 750 minus 25, to get our delta T, which is 725 degrees Celsius. So the delta T that I'm going to plug in is 725. You do not have to change things to Kelvin for this unit. You can leave it in Celsius. You do not need Kelvin for this unit. Now to solve for Q, all we have to do is multiply these three numbers. So you can even use a calculator, because I am so generous. I'm not even asking you to do this by hand. 7 times 0.46 times 725 is 2,334.5 joules. They also ask, is it endothermic or exothermic? Well, if we go back and look at our notes on this previous page, when something's endothermic, its Q will be positive. When it's exothermic, its Q will be negative. So we just found Q, and it was positive 2,334.5. So since this is a positive Q, this is going to be endothermic. Okay? Let's look at number 3. I'll skip number 2 for now. Let's look at number 3. Number 3 says a 30-gram sample of an unknown metal. So this 30 grams, that's our mass, is cooled from 59.2 to 22.5. So this is our initial, and this is our final. Because it starts at 59.2, then it was cooled to 22 degrees Celsius. It says during the process, 1,000 joules of energy, so this is Q, is released by the metal. When it's released, that means it's lost. If you're losing heat, then guess what? This 1,000 joules is actually negative because it's being released. It's getting lost. So we have to read the problem to check and make sure that this is a negative or positive amount of heat. And because it's released, it's lost. This is actually going to be negative when we put it on our guess boxes. Which is why I picked this problem, so we can talk about that. So if we fill in our given box, we have a mass of 30 grams. We have an initial temperature of 59.2 degrees. We have a final temperature of 22.0 degrees. We have a Q of negative 1,000 joules. And they're asking, what is the specific heat of the metal? So they want to know for what is C. So our unknown is C, specific heat, which always has units of joules per gram degrees Celsius. That's those units are, again, right up in our chart over here. So that's joules per gram degrees Celsius, and my answer needs to be joules per gram degrees Celsius. Okay, we're going to start plugging stuff in. Our Q is negative 1,000. Don't forget the negative. M is 30. C we don't know, so that's going to stay a variable. You could also write X there if that makes you more comfortable. Again, for delta T, we have to do final minus initial to figure out what that term is. So delta T is going to be our final 22 minus the initial 59.2. So we're actually going to end up with a negative temperature change. A negative temperature change. What does it mean if the temperature change is negative? If something's changing in a negative way, all that means is it's going down. That's fine for your temperature change to be negative. That just means the temperature is going down. So negative 37.2 is going to be our temperature change that we put in this box, because it's cooling down, which should make sense. They say in the question that it's cooling. They also said heat's getting released, so the heat's going down. That means the temperature should probably be going down too. That makes sense. Okay, to solve this, the first thing we want to do is combine our like terms. So we can do 30 times negative 37.2 on the right side. That's negative 1,116. That is still going to be times C, specific heat. So to solve for specific heat, to solve for C, I need to isolate C by dividing by the negative 1116. If I do that on the right side, I have to do it on the left side. And that comes out to be positive 0.896. Positive 0.896. They also ask if in this question if it's endothermic or exothermic. Remember, for endo and exothermic, we have to look at the Q. In this problem, our Q was negative. We had a negative Q. Heat was being released. When heat is being released, that's exothermic. Okay. At this time, you have 4 other problems to do. So, get to work.